All right, so welcome everyone to the Pseudorandom Functions session. So let's get started. So we'll have two talks in this session. And our first talk will be on privately puncturing PRFs from lattices, adaptive security, and collusion-resistant pseudorandomness. And Rupon Yang will be giving the talk.
Yeah, thanks for the introduction. Hello everyone, I'm Rupon Yang from the University of Wollongong, and today I'm glad to share our recent work on how to construct a private puncture PRF with both adaptive security and collusion-resistant pseudorandomness from standard lattice assumptions. So a puncture PRF is a special case of a constraint PRF, and roughly speaking, a constraint PRF is a PRF family that allows one to derive a constraint K from a PRF K. The constraint K is associated with a constraint, and it can be used to evaluate the PRF on any input X that satisfies this constraint. On the other hand, if the input X doesn't satisfy the constraint, then the PRF evaluation on X will be hidden from the constraint K. So sometimes we may need an optional security property called privacy. That is, the constraint K will hide the constraint. And this constraint PRF with this security property is called private constraint PRF. So with define security, our constraint PRF, we usually consider the authorities that can make some Oracle queries. So to make things more concrete, we will consider this very basic security definition for the pseudorandomness. In this definition, the challenger will first sample a PRF K and sample a bit B. And then the adversary should submit a challenge query X star, which is an input, and a K query C, which is a constraint. Then the challenger will generate a constraint K for the constraint C. And it will set a string Y star as either a random string or compute it as the PRF evaluation on the challenger input X star. And then it returns the constraint K and the string Y star to the adversary. And then the adversary will make some evaluation Oracle queries. That is, the adversary submit an input X and get the PRF evaluation on the input X. And the adversary is finally should submit a bit B prime, and it wins if B prime is equal to B, and B can't be trivially learned from the Oracle queries. So that is, the challenge input X star should not satisfy the constraint C, and it should not be submitted as an evaluation query. So in this definition, the adversary must make a K query and a challenge query before making any evaluation query. So that is, the order of the Oracle queries should be predefined, and this is usually denoted as selective security. Also in this definition, the adversary can only get one constraint K. So this is usually denoted as 1K security. So this is the basic definition of selective 1K pseudorandomness. And in a similar way, we can define the selective 1K privacy. The two security definitions are satisfied by all the circuit constructions of constraint PRFs or private constraint PRFs. However, they may not be sufficient in many applications, and we may need some stronger security properties. One such strong security property is called adaptive security. That is, it allows the adversary to make the Oracle queries in an arbitrary order rather than the predefined order. So we have constructions of adaptively secure constraint PRFs for various constraints from indistinguishable obfuscation. But if you somehow don't want to use obfuscation, for example, if you hope to have post-quantum security from standard lattice assumptions, then the only constraint that you can support is the constraints that can be implemented by the inner product predict. Also, we can consider the collusion resistance for constraint PRFs. That is, the adversary can get more than one constraint case. So again, you can have many constructions of collusion-resistant constraint PRFs or private constraint PRFs from obfuscation or multilinear maps. But if you restrict the assumption to be standardized assumptions, then the only constraints that can be supported are those can be implemented by the inner product predict. So the situation raises the question that can we achieve either adaptive security or collusion resistance from standard lattice assumptions for beyond the inner product predicts. So in this work, we solve this problem, or we narrow the gap by providing the first construction of private puncture PRF with both adaptive security and collusion resistance pseudorandomness from standard lattice assumptions. So we don't achieve collusion resistant privacy, but we give the first step to achieve collusion resistant pseudorandomness. So a puncture PRF is a special case of a constraint PRF that the constraint is associated with a puncture set P. And an input X satisfies this constraint if and only if X is not belong to this puncture set P. So if the puncture set P is of fixed size, for example, if it can only contain one input, we will call it one puncture PRF. So the next question is why we need to consider puncture PRF, because it seems rather limited. There are two reasons. For the first reason, as shown by PTW20, in some scenarios, it is possible to construct a constraint PRF for the inner product predict, but it is not possible to construct a puncture PRF. That is, the puncturing constraint can't be implemented by the inner product predict. So we need some new ideas to construct a puncture PRF with the stronger security properties, and these new ideas may be useful to help us to construct constraint PRF for general predicts with stronger security properties. The second reason is that puncture PRF itself is already useful in some applications, such as watermarking. Okay. So that is our main result, and next we will talk about how to achieve the result. So we proceed in two steps. In the first step, we give a generic construction that upgrade any one puncture PRF to have adaptive security. And in the second step, we give a semi-generic construction that upgrades some 1K1 puncture PRF to have collusion resistance pseudorandomness. The construction can preserve the adaptive security of the underlying construction. So next we will see how both step proceeds. So the first step needs a new primitive called expandable hash. In a nutshell, an expandable hash is an injective hash function that allows one to reprogram the hash evaluation on some channel input X star after the changer has used the hash function to answer some evaluation queries. So this is a bit like the reprogrammability of the random oracle. But here, we will review the description of the hash function after seeing the changer input X star. Also, we allow the challenger to fill with some non-negligible probability. So these restrictions make the new primitive not as strong as the random oracle, but it allows us to construct it from the standard lattice assumptions from standard lattice assumptions in the standard model. So for some reason, we are not able to cover the constructions of the expandable hash. If you are interested, please refer to our full paper for more details. Okay, so now with an expandable hash, we are ready to upgrade any one puncture PRF to have adaptive security. For one puncture PRF, as the puncture set only contains one input, and it must be the changer input due to the restriction for the definition of pseudorandomness. So we can simplify the definitions like this. Okay. So now to construct the adaptive secure puncture PRF, we simply modifying the evaluation algorithm of the underlying selective secure puncture PRF by evaluating the function the PRF on the hash of the input rather than the input itself. So this modification allows us to sample the hash of the changer input before seeing the real changer input. And then, after receiving the changer input, we can reprogram the hash evaluation to map the changer input to the string we have selected in the beginning. This allows us to reduce the adaptive security to the selective security. And the security of the expandable hash guarantees that such reprogramming can't be detected. Okay. So in this way, we can prove the adaptive security of the simple construction, and using a similar idea, we can prove the adaptive privacy of the construction. Okay, so that is the first step. We rely on a new primitive called expandable hash, and with this primitive, it is very easy to achieve adaptive security. So next, we will talk about how to achieve collusion-resistant pseudorandomness. So for collusion-resistant pseudorandomness, the dosary can get some constraint keys, and all of them will be punctured on the change input. So our main idea is to split the PRF key into several parts and puncture each part on one input. And if we can somehow puncture the same part on the change input, then it seems that we can reduce the collusion-resistant pseudorandomness to the one-key pseudorandomness. So that is how we construct how we make it in more detail. So now giving n inputs x1 to xn, so actually we can support any unbounded set as long as the set contains only polynomial inputs, but here we make it n inputs to make things easier. Okay, so now given n inputs, we will first generate n PRF keys kx1 to kxn, and each of them is derived from xi by using another pseudorandom function g. So we will also connect the kx1 to kxn with the original PRF key k by using another PRF key k0. That is, k0 is equal to k minus the sum of all the kxi's. That is, if we sum k0 and all the kxi's, then we get the original PRF key k. So next, we will puncture each kxi on the input xi. And the constraint k includes k0 and all the constraint versions of the kxi. So to evaluate the PRF with the constraint k, we will first compute the PRF on the input using k0, and then we will compute the PRF on the input using the constraint versions of each kxi, and then we sum the result up. Now, given an input x that is not punctured, and assume that the underlying punctured PRF is k-homomorphic, then the sum of the PRF evaluation on the input x will equal to the sum to the evaluation of the PRF using the sum of the keys, which is actually the original PRF key k, and the incorrectness of the construction follows. Okay. Next, we will see why the construction is secure. For simplicity, we will consider the case that there are two constraint keys and each of them are punctured on 3 points. So recall that the change input x star will be punctured in both of the constraint keys, and without loss of generality, we assume that x star is equal to x1 is equal to x1 prime. That is, kx1 will be equal to kx1 prime, and both of them will be punctured on the same input x1. So by the one-key security of the underlying punctured PRF, we have that no one could learn the PRF evaluation on the input x1 using the kx1. But we still have the remaining 6 parts in the constraint keys. But all of them can be simulated given k minus kx1, because we can sample kx2, kx3, kx2 prime, kx3 prime uniformly at random, and we can compute k0 and k0 prime using k minus kx1. So now if the PRF keys are uniform, then we can use k to mask kx1, and then we can ensure that no one could learn the PRF evaluation on the input x1 using kx1, and the collusion-resistant pseudorandomness follows. Okay, so unfortunately, we can't use the idea to prove the collusion-resistant privacy of the construction, because in the definition of privacy, we don't require the constraint case to puncture on the same input. But fortunately, we can still prove the 1K privacy if the underlying one-pocket PRF has 1K privacy. Okay, so to wrap up, we achieve our result by 2 steps. In the first step, we give a generic construction to upgrade one pocket PRF to have a data security. And in the second step, we achieve collusion-resistant pseudorandom if the input scheme is key homomorphic and it has uniform keys. Now to instantiate the generic construction, we start from the punctured PRF from PS20. The construction, it can be constructed from standard lattice assumptions, and it is almost key homomorphic, and its PRF key is almost uniform. So by the first step, we can add adaptive security to this construction, and due to the simplicity of the first construction, the new scheme can roughly preserve the key homomorphism and the key distribution of the original construction. But the scheme still doesn't perfectly match the conditions we require in the second step, but we can somehow open the construction and introduce some tweaks. And finally, we can get a construction with collusion-resistant pseudorandomness. All right, so that is our result. We give a construction of a private punctured PRF from standardized assumptions that has both adaptive collusion-resistant pseudorandomness and adaptive 1K privacy. So the main open problem is therefore how to extend the ideas to achieve collusion-resistant privacy, or how to extend the construction to support more general functionalities. All right. That's all. Thanks for your attention, and I'm happy to take your questions.
Great. If you have questions, please come up to the microphones. Shweta?
Hi, thanks for a very nice talk. So with regards to your second open problem, like even 2 key private constraint PRF implies I/O.
Two key private constraint PRF for general constraint apply IO, but we can maybe achieve some,
Yeah, so that was going to be my question. So for general constraints, if you ask for privacy and collusion resistance, this will imply IO. But maybe for restricted classes of constraints, you can hope to achieve it. So with your construction, what do you feel? So right now you're only looking at puncturing constraints. What do you think are natural classes that your techniques could be generalized to?
Actually, the paper has 2 main techniques: the adaptive security and the collusion-resistant. Yeah, I think the collusion-resistant technique may be applied for more general constraint. I guess it can be, but maybe it can't be used to achieve collusion-resistant private constraint PRF, because the technique for collusion resistance doesn't apply to the privacy property. So for the adaptive security, currently I think the techniques can only deal with the puncturing constraint, because it will map one input, the evaluation of one input to a predefined value. So it seems only work for the puncturing or the point function.
Okay, thanks.
Thank you.
One more question for you.
You mentioned the application to watermarking and searchable encryption. So what kind of improvement did you get for watermarking?
Okay, so the paper can, so the paper gives the collusion-resistant private punctured PRF, and we can upgrade it to be a collusion-resistant private to a program PRF, I think. Okay, so also we can extend the techniques to be to achieve collusion-resistant extrapolable PRF, and this will give rise to a new way to construct collusion-resistant watermarkable PRF. And another potential application might to apply the adaptive secure private program PRF or extract PRF to construct watermarking schemes with new properties, that is adaptive security. Yeah.
Great. Let's thank the speaker again.
Thank you.
All right, so our next talk in this session will be on constrained pseudorandom functions from homomorphic secret sharing by Geoffroy Coutu, Pierre Mayer, Alain Passogou, and Mashid Riania. And Mashid will be giving the talk.
Okay, hi everyone, I'm Mashid, and I'll talk about our paper, Constrained Pseudorandom Functions from Homomorphic Secret Sharing, which is a joint work with Geoffroy Coutu, Pierre Mayer, and Alain Passogou. So as the title suggests, in our work, we construct constrained pseudorandom function. And I start by recalling what a pseudorandom function is. So a pseudorandom function, by definition, is a deterministic keyed function that is computationally indistinguishable from a truly random function. What it basically means is that the set of outputs of such a function is computed by a master secret key. And then from the point of view of an adversary who doesn't have access to this master secret key, it all looks random or blurry. But then this adversary can issue some oracle queries to the function to get the output of the function on some inputs of his choice, while learning nothing about the other points. So a constrained pseudorandom function is, again, a pseudorandom function, so it has all of these properties. But it has an additional functionality, which is for a subset of inputs like S, we can generate a constrained key, Ck of S, from the master secret key that allows the adversary to compute the function correctly on this subset of inputs. So suddenly a subset of outputs get revealed. And then for the security, we need the output of the function everywhere else, so outside of this subset or outside of the queries that it has issued, to still look random or blurry. Now just a final comment. This constrained subset S is usually defined by a predicate. So for a predicate C on the set of inputs X, we define S of C, the constraint set, to be all of the inputs on which the constraint evaluates to 0. So this is the inverse of the previous talk. Now, in our work, we construct these things, so a constrained pseudorandom function for the class of inner product and NC1, so log depth predicates. And our construction allows for the generation of one constraint key, so for one subset. And it's selectively secure in the sense that in the security game, we need this subset S to be known before anything else. We also have some cool MPC applications that I will mention later. And so the way we construct our constraint PRF is by using another protocol that's called homomorphic secret sharing. So a homomorphic secret sharing scheme is used to perform distributed evaluation on some secret. So for instance, let's take a program P in some family of programs and some secret S. And the goal of homomorphic secret sharing scheme is to evaluate P of S. And the way it does it is it first shares this secret between two parties. So these shares can be some encoding, not necessarily additive shares. It also gives some evaluation key to each of them, and then it has them run some evaluation algorithm on their inputs with respect to this program P to get some output. And now for this protocol to be useful and meaningful, we need two properties. The first one is secrecy, which roughly states that each of these shares that is given to the parties should individually hide the original secret S. And we need correctness. So the goal of this protocol was to evaluate P of S, right? For the correctness, we need the output of each of these two parties to be actually a subtractive shares of this P of S. So Y0, which is the output of the first party, minus Y1, which is the output of the second party, should be equal to P of S. And yeah, as I mentioned, in our work, we show how to transform this protocol into a constrained pseudorandom function, which allows for one key constraint generation. And so in order to do our transform, we first recognize the useful properties of the underlying homomorphic secret chain scheme. And then we show that actually most of the existing homomorphic secret chain schemes already satisfy these properties. And therefore, we have a bunch of new constructions for such a constraint PRF with these properties. And then we revisit applications of homomorphic secret chain scheme with these properties that we recognize to secure computation. In particular, to secure computation with silent pre-processing and secure computation with sublinear communication. Now let's see how we do our transformation. So let's consider constraint C and the constraint set S. So we want the adversary, so we want some constraint PRF, which allows the adversary to evaluate the function on this constraint subset S of C without learning anything else. Now the idea here is to take a PRF, so a normal PRF, F, with key K, and then to use a homomorphic secret chain scheme to compute this special program. So the program is parameterized by X, by the input X, and it takes as input the PRF key K and the constraint predicate C and evaluates to C of X times Fk of X. So what's it look like? So in order to compute our program in a homomorphic secret chain scheme, what we need to do is to first share these inputs between two parties. So we share the constraint and the PRF key between two parties, and we give one part of the shares to the master secret key holder, and the other part to the adversary or the constraint key holder. And we give each of them also the corresponding evaluation key. We have them run the evaluation algorithm of the homomorphic secret chain scheme with respect to our special program to generate some output. And then we call the output of the first party, so the output of the master secret key holder, to be the output of our constraint Pseudorandom function, and the output of the adversary to be the output of the constraint evaluation. Now, why is it working? So since the HSS scheme provides correctness, it means that these outputs are actually subtractive shares of our program. Now, for an input X that is inside of the constraint set, our program evaluates to 0 because C of X is equal to 0. So these two shares are subtractive shares of 0, which means that they are equal. So in this case, the adversary evaluates the same thing as the output of the function. And for an input that is outside of this constraint set S, our program evaluates to Fk of X because C of X is equal to 1. And in this case, y0 minus y1 is equal to Fk of X. And in particular, y0 is equal to y1 plus Fk of X. So y0 is what the adversary evaluates. And therefore, y1 is what the adversary evaluates, and y0 is the output of the function. So the output of the function looks random from the point of view of an adversary because k is hidden due to the security of the homomorphic secret chain scheme. So in this case, the output of the function looks random from the point of view of the adversary. So it looks like everything is working. We are satisfying the properties of a constraint Pseudorandom function by doing all this. But as usual, it's not the case so soon. So here, the master secret key depends on the constraint predicate C because of this first share that we are giving to the master secret key holder. And this shouldn't be the case, right? Because the output of a constraint Pseudorandom function should be evaluated independently of whether the adversary is going to issue a constraint key query or not. So now the question is how to generate this first share without knowing the constraint C. And in order to answer that, let's take a deeper look at what really happens when we do our transformation. So in homomorphic secret chain schemes that support our program, or in general NC1 programs, so log depth circuits, here is what happens. So in order to compute a program, we share the inputs, but the way we share the inputs is actually giving identical ciphertext to both of the parties, okay? So here, the problem becomes more evident because here the encryption of the ciphertext, the input of the constraint C depends on the constraint C and cannot be faked. So now let's take a deeper look at what happens in the evaluation algorithm of the homomorphic secret chaining scheme. So in the evaluation algorithm, as mentioned, the inputs are in form of ciphertext, and we have also an evaluation key. And we have some special operation, which is conversion. So you can convert an input, which is the ciphertext, into a memory value. So you can view it as just loading an input into memory. And it should be such that if you look at the memory values of the two parties, they should form subtractive shares of what they represent. So if you convert an input of C, which is an encryption of C, into memory shares, they are actually subtractive shares of C. And just a final note on how this conversion happens. So we have a second algorithm that is multiplication. And it can specifically only happen between an input value, so an encryption, and a memory value share, a subtractive share, and it outputs the subtractive share of the multiplication that these two values represent. Now, it's easy to see that the conversion algorithm can be translated to multiplication between the input that we want to convert and the share of 1. Okay, now let's go back to the fact that memory values were subtractive shares of what they represent. So here it's good news, right? Because one of them can be faked. In particular, for the constraint C, in the master secret key shares, we can generate some random value as the memory value of C. And then after we know the constraint C, we can set the memory value of this constraint in the constraint key to be the complementary share. Okay, so there's some hope, because now we just generated something that is related to the constraint in the master secret key part without knowing the constraint. So it turns out that this simple observation is actually helping us to solve the problem of constraints random function for inner product constraints. So for inner product constraints, our program changes to this. So we have a vector z, and the program evaluates to the inner product of z and x times fk of x. And the adversary should be able to compute the function on inputs that are orthogonal to this vector z. Now, the way we do it, based on what we just saw, we put shares of this constraint vector z into master secret key and the constraint key. So we can set the share that is inside of the master secret key to be a random value, and the part that is in the constraint key to be the complementary share. We also give each of them the original homomorphic secret sharing inputs of the key K, together with the evaluation keys. Now, why does it work? Because naturally we would need an encryption of Z. So here we go back to the fact that the conversion of an input into memory value was actually multiplication between the input and the share of 1. And what we say is that if we extend our evaluation algorithm, so the evaluation algorithm of the homomorphic secret sharing, to be such that this conversion is defined to be the multiplication of the input that we want to convert with the share of this constraint vector z, then if we convert a value, so a ciphertext like encryption of m, we actually are multiplying it by a share of z. So what we get is the share of m times z. So it's like we already multiply every memory value by z. And in particular, if we could compute a share of fk of x from an encryption of x, which was the case because of the correctness of the homomorphic secret sharing scheme. Now, by this new definition, we can compute a share of z times fk of x, and by linearity, we compute a share of z times x times fk of x, which was our program. So in this case, everything is working. This is the construction for constraint PRF for inner product constraints. Finally, the construction looks something like this. And the share that we give to the master secret key holder was a random value, as I said. This was the point, because we wanted to be independent of the constraint Z. Also, the share that we give to the adversary as the part of the constraint key is also only a share of Z, so it doesn't have to know the whole constraint vector Z. And therefore, it satisfies the notion of constraint hiding, which is useful in some applications. Now let's just take a quick peek at what happens for NC1 predicates, so for log depth circuits. So the idea is exactly the same. We have our program that I described before. And the problem was how to generate this a share of the constraint C without knowing C, because we couldn't put an encryption of C into the master secret key. And here what we observe is that in some homomorphic secret chain schemes, in the encryption algorithm that they use, we can partition the ciphertext into two parts, so a message-independent part and a message-dependent part. And we give the message-independent part to the master secret key holder, and the whole ciphertext, together with the constraint predicate C, to the adversary as a part of the constraint key. So here we are giving the whole constraint to the adversary, so it's not constraint hiding anymore. And then we have each of them to run some separate, different evaluation algorithms on their special shares to get memory values, so subtractive shares of C of X. And then from these shares of C of X and an encryption of K, so an input of K, we use the same idea that I explained before to evaluate a share of C of X times Fk of X. So that was it. To conclude my talk, we showed that homomorphic secret chaining scheme with some level of programmability implies constraints to random function, especially for, in particular for inner product and NC1 predicates. We therefore have some new constructions of constraints to random functions from these 5 assumptions that I will not read out loud. And in the end, we revisit applications of homomorphic secret sharing to secure computation, particular to secure computation with silent preprocessing, where one party can do all the preprocessing even before it knows the identity of the other party, and one-sided statistically secure computation with sublinear communication, which wasn't known before without fully homomorphic encryption. That's it. Thank you very much for your attention.
Great. So we have time for a couple questions. So if you have one, please come up to the microphones. Yeah. If you have a question, please come up to the mic.
For this interesting application of homomorphic sharing, I want to ask if the assumption is based on DCR or LWE. I mean, the underlying hard problem has a trapdoor, and the evaluation key, from the evaluation key to the public key, there is a comparison mapping. Then maybe your scheme can support multi-key constraint, right?
So I didn't get, so from the evaluation key, so if the evaluation key, is it actually subtractive shares of the secret key of the encryption scheme that the homomorphic secret chaining is using?
Yeah. I mean, if there is a trapdoor, then, and also the mapping from the secret key to the public key is a comparison mapping, then there are many secret keys for one public key. And then you can find, with the trapdoor, you can find many secret keys. And the master secret key is given every time you constrain the PRF, you can generate one, every time you constrain the PRF, and every time then you generate a different secret key for the whole homomorphic sharing scheme, and then sharing, for the sharing, the master secret key is always the same, and then you can constrain for each, every time. Yeah.
So our construction only allows for one constraint key.
Yeah.
So we can only generate one. If we have two, we can recover the secret key of the encryption scheme. Yeah, if that answers your question.
Okay, thank you.
Sure.
Any other questions?
Hi, thanks. So I have one kind of question that I was a little confused over on the setup. So for constrained PRF, you want to be able to evaluate on several different X's, right?
Yeah.
But it seemed to me that once this master authority like going back to your very beginning slides,
Yeah.
wasn't X sort of already plugged into it and hardwired into it?
Oh, no. So here, for instance, the program P is parameterized by X. So when you run the evaluation algorithm of the homomorphic secret sharing, you can give as input the input X that you want. Yeah.
Okay, and the person doing the evaluation has both of these things? Or?
Yeah.
Okay, so it has both for the master and for the one below it, and it can do the eval and it's still secure?
Yeah.
Okay.
Yeah. So the input X is not fixed. So the input X is a variable that, it's a function,
Okay.
so you have to
So I would have
evaluate.
EK0 and I could run it on any X?
Yeah, exactly.
Okay.
Great. Any further questions? I have one quick one. So I guess you got constrained PRFs for NC1 because you used an HSS for NC1.
Yeah,
If you had an
exactly.
HSS for p-poly, would you get constrained PRFs for general circuits?
Yeah, I can imagine.
Great. Any other questions? No, let's thank the speaker again.
Thank you.
And this concludes the session.